Hey, what's up, guys? This is Chung here again. So, LeetCode number 1948, delete duplicate folders in system. Right. So this one, basically we're given like a bunch of path, right? Where the path is an array representing an absolute path to the ith folder in the file system, right? For example, this 123 represents the path, this one, right? And then we're defining like identical word terminology here. So if they contain the same non-empty set of the identical subfolders and underlying subfolder structures, and then basically, here it try to explains what is the identical means, right? So for example, we have, okay, you know what? Let's skip this part, I think. And basically, once we identify if there are any duplicate structures, we remove all of them. Okay, and we just need to return the deleted folder structures. That's it. So for example, right? So now I think it gives you like a tree structure example. This is much easier to look at. So for this one, the I means root, right? But here we have this path, right? So we have A to B, C to B, D to A. And two folders are identical if the subfolders are identical, right? So which means that, so this subtree, so this two subtree are identical because this one A or C, they have the same subfolder subtree structure. So keep in mind that the current tree value doesn't really matter. All it matters is the subtree structure, because both this subtree and this subtree has the same subtree structure. That's why these two tree are considered to be identical. That's why in the end we'll be removing this two tree altogether, right? And after that, right, we'll all we have left is this tree. That's why the final answer is D and DA, right? And about the path here, it giving you like different path here, right? But it says if I scroll down a little bit, so for any folder not at the root level, its parent folder will also be in the input. So which means that you can consider this path it's valid. Basically, the path includes all the levels, each level's path. If we have A, B, and C, right, it's guaranteed there will be like three paths in this path. At least there will be AB, right, and then there will be ABC. Okay, basically that's the what that constraint is telling us, right? And after removing these two identical subtree, we only have D and A. That's why we output D and DA, right? Remember, so we're also outputting all the available the remaining path. Right. Here's another example, right? Oh, and one more thing is that the two identicals doesn't have to be on the same level. Not necessarily on the same level, right? So which means in example 2 here, these two, right, are also considered to be identical, even though they are not on the same level, right? Again, because this one, both this one have the same subtree structure, which is Y, right? That's why we need to remove these two, and after that, the remainings are this two subtrees, right? Or two subpaths. Okay, continue. In example 3 here, basically the answer is exactly the same because there's no two identical trees. Everything is unique, right? That's why we don't need to remove anything. And then example 4 here, right? So for this one, as you guys can see, so these two trees are identical because both this tree and this tree have the same subtree structure, which is X, Y, Z, and this is XYZ, right? That's why after that the entire tree will be removed, right? And then last one, right? Last one is exactly for the same one, but the only difference that now we are adding like a different branch. We're modifying the right tree a little bit. We're adding like a W to one of the child of B. So now this time, these two are not identical anymore because we have XYZ. This one has XYZW, right? But still, right? So now this XY and XY, these two are identical, right? Because these two have the same subtree structure, which is Y. You know, remember. So again, right? So the current trees, the current subtree's root value doesn't really matter. So this one, it doesn't really matter if this X or X1 or A. It doesn't really matter as long as the subtree structure are the same, right? All right, cool. And then the constraints, right? So we have bunch of constraints and this one, right? So the total, basically the total path or the total node, right? In the tree, it's like 2 times 10 to the power of 5. Okay. And yeah, obviously this one is a tree problem, right? And I think that the intuition is pretty straightforward. So basically, I think we already figured out. I think the first thing is that we have to somehow to represent a tree structure, a subtree structure, and then we need to save that subtree structure to to a hash table or to a dictionary, right? Along with where the key will be the serialized value of the tree, because we need the serialized value to uniquely identify a tree structure, right? Okay, so to identify a tree structure, a common way is to serialize that tree, right? Basically, we convert that tree structure into a string, and then we use that string to uniquely identify a tree structure, and then we're gonna store that the tree structure into a dictionary where the key will be that serialized value and the value will be the node, right? And then after that, basically we're gonna loop through each of the node and we're gonna serialize each of the subtree into that. And after that, we're gonna do another check to look for if there's any serialized string who has more than one node associated with, right? Because that's when we need to delete all that nodes, right? Because we have find a duplicated like the serialized tree structure, right? And after that, we can simply just remove that. To do that, and then we can just simply add like a deleted flag into the node, right? And then once after marking the deleted nodes, then we can just do another like DFS traverse to find, basically to get the deleted result, right? Yeah, so I think that's the basic idea, right? And so to build the tree structure, we can use like a trie, right? Basically prefix tree, right? So for that, we just need a node, right? And then define init. So let's create a tree node first. So this one, we're gonna have a self.children, right? This one is gonna be a dictionary, right? And then, like I said, we also need a flag to tell us if this node needs to be removed or not, right? Okay, so that's that. And so first thing first, right? We need to build the trie. Okay, so to build the trie, we simply just do we can do this, right? So for path in path, right? Basically, for each of the path, we do what? We do so the current will be the root, right? And then for C in path, okay, for this one, we have if C not in current dot root, right? Let's do this. Let's do gonna have insert, okay, instead of path. right? So this one, current equals to root, right? For C in path, right? And we check if C not in the current.children, right? So this is all part of the prefix tree template, right? We do a current.children, right? Dot C equals to the node, right? And then we do a current equals to current.children, the C, right? Basically here we just simply do this, right? I mean insert of path, right? So that's how we build the prefix tree, right? So now we have the prefix tree, right? The second one is to what? We need to serialize all the subtrees, right? Serialize all subtrees. Okay, so to do that, let's create another helper functions. I'll just call it serialize. Serialize current. Okay. To serialize the tree, remember, keep in mind that the current value doesn't really matter, right? All we care is what? All we care is is a subtree structure. That's why when we do the serialization, right? I mean, so we have an answer here. We should not include the current dot value. So what we should do? We should do this. So for all the children, right? So for key and value in the current dot children dot items, right? So here, the in the key is the node value, right? Is a node string, right? Value is a node, right? So that's the so that's why the answer will be what? Will be the key plus the serialize of the v, right? Basically, what we're serializing here is that except we're only serializing the child child structure, which means we need to include the string, okay, the string of the child node first, and then plus whatever left, right? Plus everything that's under that child node, okay? Because since we cannot include the current value, that's why we have to serialize it in this way, okay? And then here we just do a if answer is not empty, right? We're gonna store this key. Okay, to store that we also need like another dictionary. So for this one, we also need a root here. So root is gonna be the node, right? And we also need like a tree structure. So I call it tree. It's gonna be a dictionary of list, right? So here we're gonna serialize the root, right? And after that, right? Not after that. So here when serializing it, so whenever the answer or the key is not empty, we're gonna insert that into the trees dictionary, right? So where the key will be the answer, right? And then the value will be the node, the current node. Right? So this one basically stores the pattern, the tree structure, right? Key. The key is is a serialized, right? Serialized tree, serialize subtree string, right? Value is the node, is a root node. for the subtree, right? I think here just to serialize this value will be enough. If you were like to really serialize and deserialize this subtree, probably we need something more than just a concatenation of the string. Probably we need something like a separator. Like maybe we can add like a parenthesis, and then once this is done, probably we need to have like a separator, maybe like a comma, right? To identify this is the end of like a value. Otherwise, here we're only serializing it, but after serializing the subtree into a string, there's no way to deserialize it without adding any separator, right? Because it's all one string. But since our purpose of this problem is just to simply serialize the tree, not but we don't need to deserialize it. That's why we can simplify this serialized logic a bit without adding those kind of separators and parentheses maybe, right? Um, yeah, so now we have serialized the tree, right? And we have stored all the serialized tree into this trees dictionary. Next step is to mark all duplicated tree, all subtree, right? Who has the same structure, right? So to do that, we can simply do this. We can do a for nodes, right? For nodes in tree start values, right? Basically, we simply check if the length of the nodes here, if the length of the nodes is greater than 1, right? That means that everything inside this list needs to be deleted. For node in nodes, right? We simply do a node dot deleted equals to true, right? Now finally we can do our output, right? So first we need the answer. Second one, we need another DFS, right? To do the output. Now we can just pass in second parameters here to do the output, the DFS. Okay, so the last one is the DFS here. So DFS of the current, right? Let's see the current again, right? So we have to, so for key and value in current.children.items, right? So the value is the node itself, right? So basically, if the node is not deleted, right? So if the node is not deleted, and then we do a DFS of the v, right? It's going to be the node, and then the path will plus this k, right? Because remember the key is the is a string itself, and the value is the node, right? Okay, and then here if the path is not empty, right, we append this path into the final answer. Okay, and I think that's it. Right, so this is the traverse the tree to get remaining folders, right? Oh, okay, I know. I forgot to return this key here, right? The serialize key here. Yeah. Path. Okay, so this one accepted. Let's see. All right, so it worked, right? yeah, I think that's it, right? I mean, the implementation is a little bit non-trivial, a little bit long, but I think the concept is pretty straightforward, right? The only thing is that the only we have to be we need to realize that we need to somehow serialize or somehow to to store that tree structure into some like dictionary, right? And a common strategy is to serialize that tree, right, into a single string, so that we can use a string to represent the tree structure, right? And again, like I said, since for this problem, all we need is to serialize, not deserialize. That's why we can simplify the serialize function to not include any separators, right? So that's why we can simply just concatenate everything into a string, right? And then yeah, and other than that, is you just build the prefix tree, and then serialize, right? And then the next one is a mark out subtree who has the same structure to be deleted, and the last one is just to traverse it one more time to get the final answer, right? Because this way, we don't need to. Basically, we can cover all the scenarios, even with the different layers, because our key in the tree structures are the keys is the path is the serialized tree string, and the value is a node, right? Um. Oh, and time complexity maybe. Time complexity. Let's see. Um. So first things we build the prefix tree, right? To build the prefix tree, oh yeah, I think if we scroll down here, so the total of the path is like this one. Let's say this is n, right? So to build the the tree, it's gonna be n, right? And then to serialize the subtree, uh, I think this one is like basically the same tree structure, right? And then it's nothing fancy, right? Because here, we might have include multiple. This one basically has the more, will definitely have more nodes, right? Because like for example, with A, would have more nodes. No, actually no. So basically, this one will have the same nodes, the number of nodes in the tree, right? And then basically to serialize, we need to uh, we'll traverse to all the trees, all the nodes, right? And then for this string concatenations, um, so this one, I I'm not I'm not quite sure about time complexity for this part. Because the string concatenation is supposed to take about O of n time, maybe. Hmm. It's because the time complexity for the string concatenation is what is, let's say this is n1, this is n2. It's going to be n1 plus n2. That's the time complexity for this, right? And but the thing for the k here, even though the total one is n, right? But let's say the last one, right? So let's say the last one on the very leaf side is pretty long, right? It's like 500, right? It's 500, and then which means that for each of the child, let's say this one has like the let's say we have a b c d, right? And for the last one we have a huge huge subtree value here, right? It's gonna be what? It's gonna be like 500 long one, right? And even though the total is if it's in this, but for the hashing, as you guys can see, to hash the A subtree will concatenate 500 in the end, right? And to concatenate B sub to serialize B subtree, we'll also need to concatenate 500, so on and so forth. C and D as well. So I think for the serialized, for serialization, this one will be more than n, but to what extent, I'm not quite sure, right? And let's say with this kind of extreme case, right? So I think I'll just stop there, since I don't have any clue about the time complexity. And then so that's the serialization. And then for the DFS, so for DFS, pretty straightforward. This is definitely O of n, right? Because we will only traverse each of the node once, right? Assuming there's no deleted node at all, right? Yeah, I think that's it, right? I mean, this one, I don't know. It's not a very tricky one, but the implementation is a little bit long, right? We have to build the prefix tree with like a flag, and then we also need to somehow serialize all the subtrees, and then mark all the subtree who has the same serialized string, right? And then we do another DFS in the end. Cool. I think that's it for this one, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.